The power of optimization algorithms in modern computing. In today's data-driven world, optimization algorithms serve as the backbone of countless technological innovations, from machine learning models to logistics networks. These algorithms enable systems to find optimal solutions efficiently amid complexity and uncertainty. Whether minimizing costs, maximizing performance, or balancing resources, they form the foundation of smart decision-making. At their core, optimization algorithms leverage mathematical principles and computational techniques to navigate vast solution spaces. By iteratively refining candidate solutions, they address problems ranging from route scheduling to financial portfolio management. Their adaptability makes them indispensable tools for developers and researchers alike. Understanding the fundamentals of optimization. An optimization problem typically involves finding the best solution among many possibilities based on predefined criteria. This process relies on objective functions that quantify desired outcomes, often subject to constraints that limit feasible choices. Key components include variables, objectives, and constraints that define the problem domain. The choice of algorithm depends heavily on whether the problem is deterministic or stochastic, convex or non-convex, and continuous or discrete. Deterministic problems yield predictable results, while stochastic ones require probabilistic approaches. Convexity ensures smooth landscapes with single optima, simplifying convergence compared to non-convex counterparts. Objective functions, central to any optimization task, these functions measure how well a solution meets target goals. They may represent cost, time, error rates, or other quantifiable metrics. Minimizing or maximizing this function drives the search for optimal configurations. Constraints. Real-world problems often come with limitations such as budget caps, resource availability, or physical laws. Constraints shape the solution space, guiding algorithms toward viable options without violating these boundaries. Feasibility. Solutions must satisfy all constraints to be considered valid. Infeasible candidates are discarded during iterations, reducing computational overhead. Pareto optimality. Some problems prioritize trade-offs rather than singular objectives, requiring multi-objective optimization strategies to balance competing priorities. Categorizing optimization algorithms. Optimization algorithms fall broadly into three categories: gradient-based, meta-heuristic, and direct search methods. Each class addresses different problem types, leveraging distinct mechanisms for exploration and exploitation of solution spaces. Gradient-based methods. These rely on derivative information to guide descent or ascent along objective functions. Techniques like Newton-Raphson and conjugate gradient excel at convex problems but struggle with discontinuities or high-dimensional spaces. Meta-heuristics, designed for non-deterministic problems, these include genetic algorithms, simulated annealing, and particle swarm optimization. They mimic natural phenomena to explore vast search areas, favoring global optima over local minima. Direct search methods, suitable for black box or noisy environments, these do not assume analytic derivatives. Derivative-free techniques such as Nelder-Mead-Simplex operate purely on function evaluations, offering robustness against irregular landscapes. Stochastic versus deterministic. While deterministic algorithms guarantee exact answers under ideal conditions, stochastic methods introduce randomness to escape local traps and discover potentially superior solutions in rugged terrains. Applications across industries. From supply chain operations to artificial intelligence, optimization algorithms permeate diverse industries. Logistics companies optimize delivery routes to minimize fuel consumption and delays, whereas manufacturers adjust production schedules for maximum throughput. Healthcare. Hospitals utilize linear programming to allocate medical staff and equipment efficiently. Genetic algorithms assist in drug discovery by evaluating molecular interactions systematically. Finance. Portfolio managers apply quadratic programming to balance risk and return ratios in investment decisions. Reinforcement learning integrates optimization frameworks for dynamic trading strategies. Engineering. Structural engineers simulate stress distributions via finite element analysis optimized by adjoint methods. Aerospace firms design aircraft wings using topology optimization to reduce weight while maintaining strength requirements. Machine learning, neural network training hinges on backpropagation, a specialized gradient descent variant, to refine model weights iteratively. Bayesian optimization accelerates hyperparameter tuning in deep learning pipelines. Evaluating algorithm performance. Assessing the effectiveness of optimization algorithms demands both qualitative and quantitative measures. Success indicators vary depending on problem contexts but generally encompass speed, scalability, reliability, and adaptability. Convergence speed. Metrics like number of iterations or wall clock time gauge how quickly an algorithm reaches near optimal solutions. Faster convergence reduces processing costs significantly in time-sensitive applications. Solution quality. Comparisons against known benchmarks determine proximity to theoretical optima. Statistical significance tests validate superiority when empirical results show consistent outperformance. Robustness. Algorithms must handle noise resilience. Perturbations affecting input parameters shouldn't drastically alter outputs. This quality becomes critical in unstable environments prone to measurement errors or system fluctuations. Scalability. As dataset sizes grow exponentially, algorithms must scale gracefully without exponential increases in computation times. Distributed computing architectures mitigate bottlenecks arising from increasing dimensionality. Tackling challenges in algorithm implementation. Implementing optimization algorithms presents hurdles such as avoiding premature convergence, managing memory usage, and handling parallelism effectively. Developers must carefully tune parameter settings for stability during execution phases. Avoiding local minima. Many landscape structures contain multiple optima, trapping greedy approaches prematurely. Introducing random perturbations or hybridizing methods enhances exploration capabilities before settling into final selections. Computational complexity. Non-polynomial complexities pose scalability issues, especially for combinatorial problems involving NP-hard characteristics. Heuristics provide approximate yet sufficiently accurate results within acceptable runtimes. Parameter sensitivity. Fine-tuning algorithmic controls like mutation rates or cooling schedules greatly influences outcome quality. Too aggressive values may lead to instability. Conversely, conservative approaches slow down progress unnecessarily. Recent advancements and future directions. Recent years have witnessed transformative shifts in optimization methodologies driven by advances in computing hardware and novel mathematical discoveries. Quantum annealers promise revolutionary breakthroughs in solving previously intractable combinatorial challenges. Distributed computing integration. Cloud infrastructures allow simultaneous execution across geographically dispersed nodes, slashing total runtime durations dramatically. MapReduce paradigms distribute workload optimally among clusters for efficient synchronization. Mixed integer programming enhancements. Innovations in branch and cut heuristics now permit tackling larger MIP instances faster than ever before. Hybrid solvers merge LP relaxation approximations with cutting plane generation techniques seamlessly. AutoML contributions. Automated machine learning platforms incorporate optimization modules that dynamically select best practices based on historical knowledge bases, streamlining feature engineering tasks considerably. Eco-friendly algorithms. With climate change concerns growing globally, energy-efficient optimizations aim to minimize carbon footprints caused by excessive computations. Green computing initiatives emphasize eco-conscious resource allocation practices. Selecting the right tool for your problem. Choosing an effective optimization strategy requires understanding your particular scenario thoroughly. Begin by identifying whether the goal is minimization/maximization, detecting potential constraints, and assessing available computational resources. Data characteristics. Continuous versus discrete domains influence selection critically. For example, integer-constrained problems benefit from Lagrangian relaxation strategies instead of standard unconstrained optimization routines. Time budgets. tight deadlines demand quick approximation solutions rather than exhaustive searches. Approximate dynamic programming provides reasonable estimates rapidly even for complex state action spaces. Domain knowledge, leverage expert intuition to prune ineffective paths upfront. Incorporating prior experiences improves initial guess qualities substantially, accelerating overall optimization journeys significantly. Code implementation insights. Writing clean, performant implementations necessitates following best coding standards coupled with rigorous testing protocols. Well-structured libraries facilitate reuse across projects while abstracting away implementation intricacies. Modular design. Implementing common interfaces allows easy swapping between different solver engines later on without disrupting existing codebases. Encapsulating logic neatly enables easier debugging sessions ahead. Benchmarking practices. Always compare new implementations against established reference implementations using identical datasets whenever possible. Maintain version-controlled repositories tracking metric changes over time precisely. Error handling. Anticipate edge cases causing numerical instabilities, e.g., division by zero scenarios or overflow exceptions. Implement graceful fallback mechanisms whenever possible for improved software resiliency levels overall. Conclusion. Optimization algorithms empower developers to tackle intricate problems efficiently, transforming raw data into actionable insights. From simple gradient descent techniques to sophisticated quantum-inspired heuristics, mastering these tools opens doors to innovation across disciplines. To harness their full potential, practitioners should combine theoretical foundations with hands-on experimentation. Continuously stay updated about emerging trends while applying foundational concepts rigorously in every project endeavor undertaken henceforth.